Hello students, in this video we'll provide an alternate criterion for uniform convergence of a sequence of functions. Let's suppose that Fn are mappings from a set A into the real numbers. Then we can say Fn converges uniformly to a function f if and only if the numbers dn, which are the supremum of the absolute value of fn of x minus f of x for x and a, if these numbers dn tend to 0 as n goes to infinity. This is done. Okay, so let's prove this alternate criterion for uniform convergence first. So how do we prove this? So here's the proof. Suppose that Fn converges uniformly. Let me use that notation with a double arrow for converge uniformly. Converge uniformly to f on the set A. Okay. Let epsilon be greater than 0 and pick n in n such that fn of x minus f of x is less than, I can make this less than epsilon over 2, for example, or epsilon over 3, it doesn't matter. For all what? For all x and a, for n bigger than or equal to this number n capital, and all x and a. All x and a. Okay, so if this is the case, if these differences are always less than this, then the supremum of this thing over here, then let's consider then for n bigger than or equal to d, the supremum of fn of x for x and a minus f of x is also less than what? Is also less than, or equal to in this case, can be less than or equal to, epsilon over 3, which is equal to epsilon, okay? Less than epsilon, of course, strictly less than epsilon. And so that shows me that the dn, so this, of course, are dn, so in other words, dn is less than epsilon if n is bigger than or equal to n, right? That's one direction, so I've just proved that. That says that dn converges to 0, of course, right? Okay, good. All right, so now it's the other direction of this proof. So the other direction is suppose that these supremums, right? So I'm still going to let epsilon be greater than 0, and now suppose I can, now for the opposite direction, so in other words, I've shown that if you converge uniformly, so this is the forward direction of our proof. Let's do the backward direction. Okay, let's let epsilon be greater than 0, okay? And now what? And then I know that dn can be made less than epsilon if n is bigger than or equal to some n capital that we can choose. That's from the convergence. I'm assuming now the convergence of these dn's, right? And so that says the what? That says that the supremum of fn of x over x and a minus f of x is less than epsilon. And then in particular that for any x, hence for any x, that says that fn of x minus f of x less than epsilon for all x in a. Okay, excellent. And that proves the uniform convergence provided, of course, that n is bigger than or equal to n. And that's exactly the statement that fn converges uniformly to f. Okay, so in other words, it's just a different way of writing that fn converges uniformly. But it's a very, very useful technique, because now I can do some examples with this. So here's an example using this methodology. Let's look at these functions over here, fn of x, which is x to the n times 1 minus x on the set 0, 1, on 0 to 1, okay? Now, of course, as n goes to infinity, these things are going to 0. So in other words, I claim that fn converges uniformly to 0, right? So let's look at dn. So dn, so of course, if x is equal to 1, this is going to be 0. And if x is not equal to 1, like a half, for example, this 1/2 to the n is going to go to 0. So let's estimate the supremum over x in 0, 1 of this function, of the absolute value of the function x to the n, 1 minus x, right? And then, of course, I have a minus 0 because I claim it converges uniformly to 0. So I claim that this fn converges uniformly to 0. Okay? Now, how can I find the maximum of this function? Well, it's a continuous function, so let's find the maximum of it, right? So let's do the derivative. So let's call this function fn. So it's the derivative of fn. The derivative of fn of x is going to be n, x to the n minus 1, times 1 minus x, and then times negative x to the n. Negative x to the n, that's the derivative of the second term. Okay? And I set this equal to 0. And what does that tell me? Well, I can cancel out n to the negative n to n minus 1. And this is going to tell me that the supremum of this thing, so if I set this equal to 0, let's cancel this out. This is going to turn into this implies that n times 1 minus x minus x is equal to 0. So what I have over here is I have a negative nx and a positive nx. So this tells me that n is equal to n plus 1x. So x will be equal to n over n plus 1. Okay? So x is n over n plus 1. That's where the derivative is equal to 0. Now you can check the second derivative is going to be negative there, right? Because you're going to bring this down over here, you're going to see that the second derivative is negative, so this in fact is going to be a maximum, right? So this actually is the max. So let's plug that in. This is equal to, this is my dn. Okay? This is equal to n over n plus 1 to the power of n, okay? Times 1 minus n over n plus 1, okay? Now this thing over here is getting closer and closer and closer to 1 as n goes to infinity. So this thing over here is stabilizing. But what's this thing doing over here? So this is a bounded expression that's less than or equal to 1, right? And so this is less than or equal to n, this is going to be a 1 over n plus 1. And clearly this tends to 0 as n goes to infinity. So since these dn's tend to 0 as n tends to infinity, these functions fn's will converge uniformly. So these functions fn converge uniformly to 0. And that's an example of using this criterion to prove uniform convergence. Thank you very much.